Microphone. So for today, we're going to go over how you get an image out of MRI. And so last time we went over the Bloch equation, which describes how the signal evolves in MRI, how the gradients and the RF coil and the B0 field interact, and they generate a signal. And I'll just review that a tiny bit. But that last time didn't talk at all about how on earth do you get these fine-grained images, like with half a millimeter, three-quarters of a millimeter voxels, millions of voxels. How do you get millions of voxels out of the MRI? And so to understand that, we have to go over the Fourier transform, and we're going to go over it a little bit too quickly. If you want to sort of hear it at sort of a more human pace, then come to my MRI class. But it's worthwhile just sort of giving you just a sniff of how it works. It's just such a cool thing, but it's such a basic piece of math that every college educated person should know, or at least recognize it when they see it. So that's the goal today. So let's back up and just say two things about the EEG, MEG stuff, and the MRI signal, and then we'll head into image. How do we get an image? So the first thing was so if we draw one of my ugly heads here. So if we have a person that's doing an MEG experiment, we said there was some currents, and those currents were happening because the cells are elongated and they're lined up and they're stimulated at either the top or the bottom, and so the current tends to flow inside the cell rather than immediately leaking out, and that causes a little local current. Some if positive comes into the bottom of the cell, positive disappears right here, that makes it negative, and then the positive eventually erupts out of the top of the cell, that makes the top positive, and so you get that little local current flow. And so that thing is called J. So that's a vector. I just wanted to sort of emphasize what the units are. So that's the current. It's a vector because it's the current strength, that's the length of the vector, and direction, and it's going in a particular direction. That's not what we record when we record EEG. So then we said that current flowing generates a magnetic field. And how does the magnetic field work? The magnetic field works, your thumb is the current, and so it's going to be coming out of the head right here, and then going around, and then so it'll be coming out of the head here, and then going around, and then going back into the head over here. So if we draw that, so it's coming out of the head here, that's plus, like that. And then it's going into the head here, that's negative. But what does that negative and plus mean? I didn't sort of specify it. That negative and plus is actually a vector, kind of like the current. So what happens is, at this point, there's a vector sort of coming out of the head, and so that's the B vector. And then at this point, there's a vector, going into the head. This is going into the head here. So those things, those vectors, are the B vector. So that's and what is that? That's the magnetic field strength and direction. and direction. So those are both vectors. Now, it turns out in the MEG case, you can measure the vector. So an MEG machine actually either measures all three or just two components or maybe just one component of the vector, but it measures the actual directional, the strength and direction of the magnetic field. So, so that was the B and the J. But what do you record in EEG? So what you record in EEG, you got some electrodes on the scalp. And what do those guys record? Those guys record a capital V. They record the potential or the voltage. So this guy is the voltage. It's just a number, just a number. It's not a vector. It's just got, it's just a scalar. Whereas the B has three components, this XYZ component. The J has three components, XYZ. So that's just to sort of make that very clear. So you got currents that are caused by lined up cells that are getting stimulated at one end or the other end. That causes some local current flow down the length of the cell. That current flow generates a magnetic field, which is a three-dimensional thing. The current flow is a three-dimensional thing. And then you have to add up all the current flows. That's just one, but there's going to be a whole bunch of them. And then you can either record something about that vector magnetic field, or you can record just a string of numbers, a string of scalars for the voltage, or the potential. So this is the B recording is MEG, the voltage recording is EEG, and they're both caused by this current flow inside here. Okay, so that was just a review of that very first part. So a little review of the second part, just to sort of draw a picture of the T1 and T2 decay. So remember, we've got, there's the person's, we'll just draw them as a brain in there. So there's their temporal lobe. So we've got a brain in there. And the coordinate system we have like this. So that's the X and the Y, and the Z was the direction of the magnetic field. And the B0 is in that direction. That's the B0 caused by the main magnetic field. And then we've got these coils around here that are picking up the signal from the little radio wave. And so what's a picture of what T2 decay and T1 decay look like? So unfortunately, the first thing we do is we rotate the coordinate system. So we rotate the coordinate system so the Z is at the top. That's just typically the way people look at this. Or you could argue that the coordinate system has been rotated because we turned the magnet sideways. The original magnets were up and down, but now we have to have people lie in them. So what does T2 decay and T1 decay look like? So now we've got a rotated coordinate system. So we've got Y going in this direction and Z going in this direction, X going in this direction. That's just rotated 90 degrees from what you have there. And so if we start off, we go into the magnet and we start off with our local magnetization. Remember, there was M and B. B was the magnetic field that the magnet is doing, and M is the different magnetic field, which is whatever your tissue is doing locally. So if we start off going into the magnet and we get lined up at the magnet, we get slightly magnetized by lying in the magnet for a couple seconds. And then we turn on the RF, and what the RF does, the RF is it causes that magnetization to kind of precess around. And so let's say that magnetization has gotten has gotten to here. So it's precessing around that way, but at a point in time it's gotten there. Okay, so this is our M after RF coil stim. So we stimulated and lined up your protons with the RF coil, which was causing them to rotate perpendicular to this z-axis. So they start off lined up at the z-axis, then we turn on the RF coil, and it kind of makes them go around like that direction. So there they are going around. Then what does T1 and T2 decay look like? So T1 and T2 decay look like, it's the X component, the X and Y component are one of the decays, and then the Z component is the other decay, quote unquote, but it's actually a regrowth. And so what does that look like in terms of what that M vector does? So it starts off here. So this thing after RF coil stim, extremely short. So it's extremely short, so there's no time for decay. No decay. It's like microseconds, really short. So we just hammer it, no time for decay, and it's spinning around. And then what happens to it? So what it does is it quickly loses all of its XY component like that. That's the first thing that happens. And so that part is basically T2 decay. So that means it's losing the X, and we drew out the Bloch equation for that. It's losing all the X and Y component, because here's the Z component, and here's the X and Y component. So it quickly loses and that happens quickly, like, in 50 milliseconds. So like say 50, milliseconds, 20th of a second. So it quickly loses all the X and Y part of the vector. So then the vector would be a little tiny vector there. And then what happens is it takes a couple seconds. It's still sort of slightly wiggling around like that. It takes a couple seconds until it finally gets back up to the equilibrium magnetization. And so then, it finally gets back up to there. And that whole thing, that slow regrowth, that's T1 decay or T1 regrowth. It's a negative decay, also known as okay, so that's like a geometrical picture of what's actually happening in your brain. The whole thing's kind of rotated 90 degrees in the magnet, but this is usually the way they draw it. And so you quickly lose all the XY component of that M vector. So this is the M before decay. So you start there, quickly lose all the XY component, and then slowly grow up the Z component until you get back to equilibrium. And so this is equilibrium, that's MZ0. Okay, so that was just to draw out the Bloch equation, draw out what the Bloch equations describe. So they describe exactly what the numbers are, but geometrically this is what's going on. Okay, so any questions on that before we dive into the, yeah? Oh, why the decay occurs? I didn't tell you at all. So why the decay occurs is a little complicated. It has to do with the protons interacting with each other. So if they get slightly out of phase because the magnetic field in some part of the cell, for instance, is slightly higher than the magnetic field somewhere else, that will cause them to precess at slightly different speeds. And if they precess at different speeds, they're magnets. And so then these other magnets are getting pushed around by the local magnets instead of all being lined up. And so it has to do with sort of local chemical reactions, or local electromagnetic reactions between these different protons, because they're all in slightly different parts of the brain, and the magnetic field is ever so slightly different in different parts of the brain. So that's what causes the T2 decay. So yeah, so I didn't describe that at all. It was just like we wrote an equation. We started off with an equation for it, yes, and then this is what it looks like when you run the crank on the equation. But why? That's yeah. Who needs that? But yes, but that's the actual reason for why they decay. Okay, so now start off with the Fourier transform. So the Fourier transform. So the Fourier transform, which we need to understand let's just give the top view. So the top view is that the gradients are what help us make the image. So we didn't talk about the gradients at all. We just said they were in there, but we didn't say like what effect they have on the signal. And so it turns out the gradients are the main thing that's causing the data to be generated in such a way that we get a Fourier transform of the brain. So the overall picture is we collect some MRI data and then we fiddle with the gradients in such a way that we end up with a Fourier transform of the brain. Our data that spits out of the magnet is a Fourier transform of the brain. And then all we have to do is un-Fourier transform it, which turns out to be the same thing as the Fourier transform. So we just kind of do the Fourier transform again, and then we get an image out. So the goal today is to try to figure out why do we get a signal that is exactly the Fourier transform of the brain, and how do the gradients do this? So to do that, we unfortunately have to talk about the Fourier transform. So what is the Fourier transform? So at the top level, the Fourier transform is basically a way of converting between two different views of the same thing. So probably the most familiar way of sort of thinking about this is to think about a Fourier transform of an audio signal. So an audio signal, like an orchestra playing for a couple seconds, contains a lot of different audio frequencies. And so what a Fourier transform can do is it can take that time signal and then convert back and forth, because they're equivalent. They both contain the same information, into a temporal frequency representation. So it's a representation of different audio frequencies, like 4,000 cycles per second and 4,012 cycles per second. That's what the Fourier transform can do. So a Fourier transform can go both ways. You have the inverse Fourier transform, which is very similar to the forward Fourier transform, and so you can go either way. But what we're going to talk about in the case of, so I'll start off talking about it that way because, I don't know, for me at least, it's kind of, you think of sounds, there's multiple frequencies in the orchestra, and then you do a Fourier transform on it, and you get a distribution of all the different frequencies that are in that little chunk. But in the case of the MRI, what we're going to be talking about, you can do the same thing with an image. So you can convert back and forth with a Fourier transform between space, like position along the x-axis, and spatial frequency. And so what is spatial frequency? Spatial frequency is just, so what is temporal frequency? Well, if we have time, here's a particular temporal frequency. And then what is spatial frequency? It's the same thing, except that instead of, this axis is just the brightness of the image. So the brightness of the image is going up and down. So it's mathematically the same thing. So what does that look like? Well, it would look like, it's bright here, and then it's not very bright. And then it's bright here, and it's not very bright. It's bright here, it's not very bright. Bright here, stripes. It just looks like stripes. Because if you cut through that, it just goes, bright, not bright, bright, not bright, bright, not bright, like that. So that's spatial frequency. Same thing as, weirdly, same thing as temporal frequency. And so that's what we're going to be talking about using the Fourier transform to do. But we'll start off with time because, like I said, time sort of is a little more, I think it's a little more intuitive. So let's write out the Fourier transform and then just try to, so here's the Fourier transform. So we'll often use H. So the Fourier transform, so this guy is actually a vector at a particular frequency. It's a complex number. So now we have to stop for a second. So what's a complex number? So a complex number, the easiest way of thinking about a complex number is just a two-dimensional vector. So what is a vector? A vector is something that requires two numbers to describe it. And what are those two numbers? Well, one way of thinking about them is you just consider, the x and the y component. And basically the y component is the imaginary component. And the x component is the real component. So the y component isn't imaginary, it's actually a number. It's like 13, it's not imaginary at all. But that's just a funny number that has two numbers, that requires two numbers to describe it. Now you could describe it that way, or you could describe it more conveniently as an angle and then an amplitude. So you could either do it in Cartesian coordinates or polar coordinates. And most of the time we talk about it in polar coordinates. But the Fourier transform, we're writing it out in Cartesian coordinates. That's the way it's actually computed on a computer. Okay, so this thing is a complex number. So what is that? So this is for one frequency, and this frequency here is real. So that's just a single number. That's like frequency 13. But the Fourier transform at a particular frequency is a complex number. So this guy's actually a vector. It's got a real and an imaginary part for one frequency, for one real frequency. So for one frequency, and it's across all time. So that goes back to our original description of the Fourier transform. It's a way of sort of converting between time and frequency, but when we convert to frequency, that frequency just extends across all of time. So like we say, like the orchestra for this 5 seconds had such and such amount of 7,300 cycles per second in it, and that extends across that whole 10 seconds or 20 seconds, however much a sample of time you took. So across all time, or across a chunk of time. And so this guy's complex. It's a complex number. It's got two numbers to it. And so what are those? What are those two numbers? Well, they're going to be like real and imaginary. It's going to be a vector pointing in some direction with a certain length. Okay, so how do we get that number, that double number? How do we get that double number? We basically just do a dot product. And what is a dot product? A dot product is you take the x component and multiply by the x component, the y multiplied by the y. Or you can also think of it as like a correlation. How do you do a correlation? You've got a bunch of numbers from column A and a bunch of numbers from column B. You multiply each pair and add them up. That's fundamentally what a correlation is. And so a Fourier transform is basically like a correlation. It's got the complex part, so you have to do at least two correlations, but it's easy to think of it as a correlation. And so what is the basic equation? It's just basically a sum across all time. So this guy just means sum. The integral is just a sum. So it's a sum across all time of two things multiply by each other. And what are those two things? So the first thing is basically our signal at a point in time. So there's frequency over there and time over there. So it's our signal at a point in time multiplied by this thing. Minus I 2 pi frequency time. So now all hell breaks loose because we got, E, how many things are there? It's like 1, 2, 3, 4, 5, 6, 7 things there. So what does that thing mean? And then finally, for each small chunk of time. But always sort of back out to the big picture. The big picture is we're just going to take a bunch of time points from our sample and then multiply them by a bunch of whatever this thing is. So both of these things are complex. So this guy is the signal at each time point. So signal at each time point. It's complex. Now you may wonder, I thought an audio signal just has one string of numbers. How could that be complex? Well, if you just stick onto the x-axis, onto the real axis, so here's the real, here's the imaginary axis. If you just stick with vectors that are on the x-axis, then, so like say here's a vector along there, and then there's another vector that's a little bit longer, and then sometimes you got a negative vector, or maybe a real long negative vector. As long as you kind of don't have, as long as the imaginary part equals 0, imag equals 0, then you have a real signal. So that's the way we have to enter it into the Fourier transform. The Fourier transform demands that this thing be complex. And so it means it has to have two parts. So all we have to do is just stick in two strings of numbers. Like one is the time signal. There's the time signal. And then here's the numbers like, 13, 12, minus 2, minus 14. And then here's another signal. That guy's all 0. So that's the real and imaginary. So that's how we can turn our audio signal into a, little did we know our one-dimensional audio signal was also complex. Okay, so we have to stick in a complex number here. But if the imaginary part is 0, that's still a valid complex number. And then we multiply by this thing. And so what is this thing? So this thing, in my younger years, when I saw that, brain explodes, like it doesn't make any sense, what is it? So what it is, it's a complex number, but it's a very simple complex number. It's a complex number that it stands for a vector of length 1. It's just a vector, length equals 1. Pointing in a certain angle. And what is the angle? This guy is the angle here. This guy is actually an angle. And there's 2 pi in there. We'll say what that is. So it's a vector of length 1. But what's another way, of really simple way of thinking about it? You can just think about it as cosine and sine. It's just cosine and sine of that angle. So the two numbers in the complex number are just the cosine and the sine. So if we go over here and draw our complex number, there's our complex number, and it has a real part here and the imaginary part there, and its length is 1. Its length is 1, and here's that angle. There's the angle that we're talking about. This angle right here. So if you think of that complex number, a number that's always 1, what is the imaginary component going to be? It's just going to be, or what's the real component? It's just going to be, the real component is just the the length, the hypotenuse times the cosine of the adjacent. That's just the sort of basic trigonometry. So it's the hypotenuse times the cosine of that angle. That's going to be the length of the x component or the real component. And what's this guy? This guy is just the hypotenuse times that's the opposite side of the right triangle. Here's the right triangle. That's just the sine. So basically this mess here just is it's just a vector of length 1 pointing in whatever angle you stick in right there. So that's so it's less fierce that way. It's just an x and a y. And what is it for? Like, why is it that way? Well, if we just sort of get rid of the minus, minus turns out to be just the minus angle. We don't have to worry about that. If we look at something like that, what is this thing? So this guy is an angle, and it's just a single number, and it's a linear variable. And what does that mean? Well, it just means it kind of goes up and up and up and up. So you can have the sine of 25 degrees, the sine of 300 degrees. You can have the sine of 17,000 degrees. It's just the angle can be whatever. It can be like a large negative number. It can be anywhere. It doesn't have to be 0 to 360. It can be 370 degrees. So that's a linear variable. And what this guy does is it basically converts lin to circular. That's the way you should think of it. And so what you get out of it, the whole thing you get out of that is a circular variable. So now we've got this, vector length equals 1 circular variable. Because it kind of wraps around on itself. And how does it wrap around on itself? Well, if you got 45 degrees, you get a certain real and imaginary. If you wrap all the way around to 360 and then add 45 degrees to 360, so you got like whatever that is, 45 degrees plus 360, you're back at where you were before. And so this is like a mechanism for dealing with something that wraps around itself, like a rotation or some kind of wave that wraps around itself. So if you do anything with any kind of waves or any kind of rotations, you'll always end up with these guys. And so what they do is they turn a linear variable that keeps going up and up and wrap it around on itself so that it just wraps around. So that's what that's for. But we can just think of it as cosine and sine. It's just a cosine and a sine. So now let's actually just write out how you would do the Fourier transform on an audio signal. And then we'll talk about a brain. So how would you do it on an audio signal? So let's start with our audio signal. We just want to operate this equation. So when you look at this equation, you have to it's just a little machine for generating stuff. And so we've got, a frequency here, but you can see the frequency is also right there. And then to get one frequency, what do we have to do? Well, we have to sum across all time. So here's time here, and here's time. So we've got to look at the audio signal at each point in time, and then but time's also stuck in there. Look at those sines and cosines at all different points in time, and then sum across the whole thing. So when you look at this, just sort of look at it, the equation as some little way of, it's a little machine for generating something. So for one frequency, what do we need to do on the right side? Sum across the correlation between our audio signal and these sines and cosines, because that thing just turns into sines and cosines. So here's our audio signal. So it's across time. So let's just take a chunk of audio signal. So there's, it's an orchestra playing. It's got some cymbals and all different frequencies in it. And we said we've got to turn it into, the Fourier transform demands a complex number. So this guy is all 0. Sort of seems like you're cheating, but just hang in there. So there's the real and imaginary part. So those are vectors that are just sticking along the x-axis of the real imaginary plane. Okay, so that's our signal. That's the HT. So now let's do a calculation for one frequency. Say like frequency 3 is the one I always use because it's easier for me to draw. So what is this? It's just multiplying a whole bunch of these times a whole bunch of these, also known as a correlation. So it's basically just correlating the frequency with a particular frequency, sine, and cosine. So let's draw out the things that we're correlating with. So the things and let's do it for, say, say cosine 2 pi frequency 3 times time. So that's frequency in cycles per second. Now, what's the 2 pi business? Where did the 2 pi come from? That comes from just the fact that it depends on what units you're using for your angle. And so one natural unit is a radian. And so what's a radian? A radian is if you've got a circle of radius 1, and you go 1 along the circumference, so you go 1 along here, then that angle is called a radian. And that's the natural unit for the Fourier transform. But the problem is, typically, we describe things in cycles per second. And so what's a cycle? So a cycle, all the way around like that, is 2 pi radians. It's just the circumference of the circle. And so that's why we always end up at that 2 pi. So you can leave the 2 pi out here and do it in radians, but then you end up with the 2 pi somewhere else. So you just, it's always going to be a 2 pi somewhere in there. Okay, so this is cycles per second. Cycles per second. And it's 3 cycles per second. And so what does that look like over time? So that looks like, if we start off with the cosine, it goes like 1, dun, dun, okay, just about right. Okay, so if we did cosine of just one cycle of 1 times time, we would end up with just a single cosine. Single cosine would look like that. But here we're doing cosine of 3 times time, and so that will give us 3 humps. So that's what this thing looks like, but the cosine part of that thing looks like, and then all we need is the sine part of that thing, which is the imaginary part. So here's the sine part of it. That's also over time, so that's sine of 2 pi times frequency 3 times time is the variable. And so that's the real and imaginary part of the E business. So this is, the E biz. This is our, audio signal. So now all you have to do is just operate this equation. Now the only problem is this guy's a complex multiply, right? So this is so now we have to multiply complex numbers, kind of a pain in the butt. So complex mult. But in the case, if we just have a real signal, it's easier. It's basically we just have to correlate that real signal with the cosine and correlate it with a sine. And so what does that mean? It's very concrete. All it means is get a number from this one and then go down and find out what the number is there. Multiply that. And then add it to this number, going down and finding out what the number is here. And then, do the whole thing for the whole mess. And so then what do? We multiply all those numbers and then sum them all up. And what do? They go to Fourier land. So here they are in Fourier land. So add them all up. And what do we get? We get the real component of Fourier transform at frequency equals 3. And what do we do for the imaginary part? Well, you take that same number, but instead multiply it by the sine. And so here's that same number. Just go down and multiply it by whatever the sine is at that point. And do that over here. So the sine at that point. And then you just add those all up. And then you get the imaginary component, which is just the correlation with the sine, basically. Imaginary component of Fourier transform at f equals 3. So those two are independent from each other. That's why you need two numbers. So it might look like a lot like a cosine. Say your signal looks like just a pure cosine, in which case it would have a big correlation here. But that tells you nothing about how much it looks like a sine. It could look a lot like a cosine. It could look sort of halfway in between a sine and a cosine, in which case it looks like both. Or maybe it just looks like mostly like a sine. And what indicates what it looks like, it's just what direction the imaginary number is pointing. So if it's pointing down here, it looks a lot like a cosine. If the imaginary number that you get is pointing this direction, it looks like a negative of a cosine. If it's pointing up, it looks like a sine. If it's pointing down, it looks like a negative of a sine, and everything in between. So basically, it's just a way. It's amazing. You can just correlate just with a cosine and a sine, and you can find exactly how much percentage of it looks like a sine and a cosine. That's the trick of the Fourier transform, because a sine is not correlated with a cosine at all, zero correlated. So that's the trick of why you end up needing two numbers to describe this. Okay, so what do we do after we get this? Well, now we're in Fourier land. So you might wonder, how could this possibly relate to the brain? But it actually relates to the brain in a very concrete. So now we're in Fourier land. And so what does Fourier land look like? It's now got frequency instead of time. So this was all time. And so Fourier land pretty much has frequency. And we can have sort of real and imaginary frequency, or more conveniently, we can have amplitude and phase frequency. So this is frequency in all cases. So what these two numbers turned into, this guy went over here at frequency 3, and then this guy went over here, the sum, at frequency 3 for the imaginary part. But we can convert that guy, from real and imaginary into, angle and amplitude. That's what we do down here. And that's kind of the more convenient way to look at it. So we say, at this point, there's that much frequency 3 stuff in there. And maybe there was some frequency 4 stuff and frequency 27 and blah, blah, blah. But at each frequency, it's not just the amount of it. We got to know the angle of it. Does it look like a sine or a cosine or something in between? And that's what this phase number is. And there'll be a phase number at 3 that will tell you, like, to what extent does it look like a sine or a cosine. Okay, so hopefully that wasn't too painful, sort of get the general gist of what's going on here. It's kind of like you take a signal and you basically correlate it with sines and cosines. And when you end up with this representation, it contains all the information that this one does. So you can actually completely convert this back into the audio signal. And that's what we'll be doing when we actually do the brain. So how on earth does this actually relate to the brain? So, and gradients. So here's how it relates. So what we want to do is end up with a signal that's a Fourier transform that has done this correlation business of the brain. So our brain is kind of like our audio signal. So let's start off where we turn on the RF, short, microseconds. So we turn on the RF, and what does that do? That sort of sweeps all the protons into alignment with each other. And so if we draw out x-axis, so this is space now instead of time, but it's like going left to right across the brain. And at each point, we've got what direction is the magnetization pointing? And if we turned on the RF for just a short period of time, we'll line everybody up and they'll all be pointing at angle equals 0. So just along the x-axis. So they're all the protons are sort of precessions are all pointing in that axis. So that's what the RF does, lines everybody up. Okay, so then, and just this is, it's definitely X. So this is just left brain, this is right brain. This is actual real space. So now let's turn the gradient on for a little while. So number 2, turn on gradient. For a little while. So what happens? So now what happens to all those precessing spins? So now we draw them out again. Now just say we happen to turn it on for it's still left and right brain. We happen to turn them on for just the right amount of time. So remember, what does the gradient do? Turn on the x gradient. It just changes the z component. So it changes the, if you look at a person in the magnet like this, here's the magnet. You're looking down on them. What does it do? It just, if here was the B0, it just makes the B0 slightly bigger on this side of the guy's head, and it makes it slightly smaller on this side of the guy's head, like that. So it sort of goes like that. It just slightly changes the B0. The B0 is much bigger than the gradient, like 50, 100 times bigger than the gradient. And what does that do? That changes how fast the little tops precess. And so the guys that are at the high end of the gradient get ahead. And so at some later point in time, after we've had the gradient on, let's just say we turned them on, say we turn the gradient on just enough to get these guys one ahead. And let's forget about the negative part of the gradient. Just say pretend we started at 0 and then went up to a positive number to make it a little easier to illustrate. So these guys will get a little bit ahead. So about halfway through, they'll be pointing the opposite direction, and then all the way through, they'll be pointing the same direction. And then they'll, this guy's a little bit ahead, and a little bit more ahead, and then a little bit more, something like that, and then it goes around the other way. Okay, so you can see, so we've wrapped these guys up just one cycle. And so what is that? That's spatial frequency 1. Okay, so now we turn, and then what we do is we record a signal. So number 3, we just record a signal. Now it's coming from the whole head. Signal from whole head. It doesn't have any space in it. So that's not where the space comes from. We just got one data point, complex data point. It's just recorded from the whole head. So how on earth do you get space out of this? Well, let's just consider, is that signal going to be big or small? And so if we first imagine, instead of a head, what if we just filled up the whole bore with gelatin? There was no head in there. It was just like one giant plug of gelatin in there. What would we get out of this? What would we get out of the RF coil? Well, it's just summing across this whole mess. And what's going to happen? They're going to cancel out. We'll get nothing. We won't get anything because they're all pointing in slightly different directions, wrapping around the circle, add them all up, tip to tail, get 0. But that's not what's in there. What's in there, there's a gelatin-filled head, and then there's some space on either side of it. So just to sort of really, bring that home. So there's a brain in here. So here's a brain. So I'll draw sort of like, there's the white matter, and this is like a coronal section of the brain. So the brain is actually in there. And so when we do this operation, the Fourier transform operation, essentially the magnet is doing a Fourier transform. So how is it doing a Fourier transform? It's basically multiplying how much stuff you have by what the angle of these spins are. So let's just do that multiplication. So if you just do that multiplication, so here's the, so these guys are all lined up. So there's brain here, and so if we look at all our little precessing protons, there's a few protons. If you're breathing, if you're alive in the magnet and breathing, there's a few protons out in the air, some water vapor, but compared to the number of protons in your head, almost nothing. And so the signal you're going to get from here is really big. And you're going to get a really big signal from, over here. And, a pretty big signal from over here, and a big signal from over here, big signal from over here. And then once you get out into the air, there's almost no protons. So those guys, there's almost nothing. And so when the head coil sums them all up, so let's sum them all up, what do we get? We get one complex number. And what is that complex number? Say it's, it might be like that. So that's, and it's got it has a real part and an imaginary part. So there's the real part here, there's an imaginary part there. So that's one data point. And what is that? That's basically one of these. And how did we do it? Well, we turned the gradient on, and the gradient did the e to the minus blah, blah, blah part. And then we multiplied it by the brain at each point. So, the brain is only here, and so you get like these big signals out of the place where the brain is, and there's just water vapor, a little water vapor here, you get almost nothing out of that. Sum the whole thing up, complex sum, that's, complex vector sum. So sum up all those vectors. And what do we get? We get one vector, one data point. It's got a real and imaginary part. And that tells us how much the brain looks like frequency 1. Now, does the brain look like frequency 1? That's a good question. What frequency, spatial frequency, does the brain most look like? Because you could have spatial frequency 2 or spatial frequency 3. And so what is the single frequency that the brain most looks like? Single spatial frequency. And let's just think about this, concretely. So here's a brain. Here's a brain. Coronal section of the brain. So what does that look like? What spatial frequency does that look like? Let's just take a line across it. And what does that line look like? Well, it looks like nothing, and then brain, and then nothing. And what frequency does that look like? That looks like spatial frequency 1. What does it look like? It looks like a negative cosine. What does a cosine look like? Cosine looks like this. That's what a cosine looks like. What's a negative cosine? Negative cosine looks like that. So, minus cos. That's what it looks like. It looks a lot like that because, it's dark, light, dark. So spatial frequency 1 is the biggest frequency. Biggest frequency there. And so then how do you get the whole, but that's kind of a blurry image, so how do you get the whole thing? You just leave the gradient on until you wrap this guy up 2 cycles and then collect another data point. And that tells you how much the brain looks like spatial frequency, how much does it look like 2 stripes. This says how much does it look like 1 stripe, a lot. How much does it look like 2 stripes? Not as much. And then you go up to leaving the gradient on long enough until these guys have wrapped themselves up like 128 times. So you got 128 stripes where it goes all the way around and then all the way around again 128 times. Does the brain look like 128 stripes? It does a little bit. So if you look at the brain, there's some gray matter and then white matter, something like that. That sort of looks like 128 stripes, a little bit, not very much, but imagine, so here's 128 stripes. And when you correlate that with the brain, there's a little bit, it looks a little bit like that. And so that's where you get all the space from. So the gradients essentially wrap up these spins, and then over time, and you collect, first 1 wrap of spins, spatial frequency 1, and then 2 wraps and 3 wraps up to 128 wraps. And once you've done that, you have you actually physically made a Fourier transform of the brain. And then all you got to do is just Fourier transform it, which is the same operation, and magically, and then you get a brain. So that's where all the space comes from. It doesn't come from the head coil at all. It doesn't come from slice select. No, it doesn't. That's not where the space mainly comes from. It mainly comes from the fact that you are arranging by turning the gradients on and wrapping up the spins to collect a whole sequence of different spatial frequencies, so that you end up with a Fourier transform of the brain, and then all you have to do is Fourier transform it, and magically you get a brain. Okay. So how did it go? Can you sort of see? I mean, we're going over it very fast, but you can sort of just get a feel for, why you need complex numbers and, these different frequencies, different stripe patterns. So, what you're doing is you're synthesizing the brain out of a zillion stripe patterns. That's basically what you're doing. You're saying, like, it looks so much like 127 stripes and so much like 126. And then you got to consider different angles of stripes. And then, you end up with those 50,000 data points, and then you Fourier transform, and you get 50,000 actual image points. Okay. So any questions about a way too fast run through the Fourier transform and how it relates to MRI? So, like I said, there's only 2 equations. That's the good news. There's just the Bloch equation that tells you sort of how the signal changes. And then there's a Fourier transform that tells you how you get the image. Okay, so I will record a lecture on Friday, so we'll do a whole lecture review of the whole class. And you don't have to come; you can just look at it online. But if you want to ask questions, and I could actually turn it on the Zoom. Should I set up the Zoom? I could set up the Zoom on on Friday if somebody wants to ask a question through the Zoom. I'll try to remember to do that. So I'll do at least an hour or more of review on Friday.